Hello everyone, the title of our paper is Novel Shaped 8016 Phase Shift Key Modulation with Improved Spectral Efficiency. I will present our research in the 4 parts: introduction, methods, results, and conclusion. Well, firstly, the content of introduction is divided into 2 parts. The first part focuses on the development of continuous phase modulation. Recently, as a spectrally efficient modulation scheme, continuous phase modulation has attracted great attention. A constant envelope and continuous phase allow for robustness against nonlinear distortion and high spectral efficiency. Due to these properties, continuous phase modulation has been widely used in a number of fields, such as satellite communications, deep space communications, and telemetry. Well, the second part is that the design of Precoder has great impact on the signal spectral property and the bit error rate. However, few research has studied on the higher order phase shift key. Therefore, we propose a novel Precoder based on 8 or 16 phase shift key. Well, next, the second part mainly presents our methods. First of all, we give the signal model in the equation 1 and the equation 2. Well, the ES is the average integer per information symbol. TS is a symbol interval. H is a modulation index. The symbols BI are drawn from the alphabet. QT is a phase smoothing response. Well, figure 1 shows the proposed Precoder. We can see that in the classic continuous phase modulation, the symbol is selected from this alphabet, and in our proposed shift 8 or 16 phase shift key, the transmitted symbol is selected from this alphabet. Well, instead of using the mapper, we propose a Precoder based on 8 or 16 phase shift key to convert the original binary bits to data symbols drawn from a different alphabet. The role of the Precoder is to orient the phase of the continuous phase modulation signal to make it behave like the phase of 8 or 16 phase shift keying signal. Compared to the conventional mapper in continuous phase modulation, the spacing of data symbols in the proposed Precoder is much smaller, you can see. Besides, the Precoder can constrain the phase change within pi. Thus, we can expect a decreased bandwidth, because we all know the more larger the phase variation, this phenomenon may cause an increased bandwidth. Well, considering the receiver, shift 8 or 16 phase shift keying can be constructed either by shaping the path of 8 or 16 phase shift keying or connecting the proposed Precoder with phase shift keying. Thus, we consider that both optimal soft decision, BCJR, and the conventional MPSK concurrent demodulator could be deployed for receiver. On one hand, after the CPM modulation, the phase of SMPSK depends on the cumulative phase of previously transmitted symbols known as the phase memory. Therefore, we assume the SMPSK information sequence as finite and ergodic state Markov sequence, for which algorithms for maximize a posterior symbol detection can be derived based on the BCGR algorithm. The transition between two states corresponds to the transmitted symbol Bn. The symbol estimation is given in equation 1, where Bn denotes the symbol transmitted in the nth time index. Up triangle Bn is a symbol estimation in the nth time index, and PBNY is a posterior probability of the received signal. The conditional probability is given as in the equation 2. The decision device chooses the symbol with a maximum posterior probability. On the other hand, we consider the receiver design based on IQ coherent demodulation. Each phase at symbol transition instance of SMPSK is drawn from the phase stage in the MPSK constellation. Therefore, we adapt the detection techniques for MPSK systems to the detection of SMPSK. Where Figure 2 compares the demodulation methods, we can see that BCGR has better BER performance than IQ coherent demodulation. This can be explained as follows. Firstly, BCGR pays attention to the distance between received signal and the possible transmitted signal in the whole time interval, while the IQ coherent method only focuses on the distance in the symbol transition instance. Hence, the former can make full use of signal information. In addition, each symbol is independent in the BCGR demodulation. Hence, we use BCGR method to modulate SMPSK. Well, the third part is about our results. The results are presented in two parts. We firstly consider theoretical performance comparison. In this paper, we use achievable spectral efficiency, ASE, which is given in equation 3, to compare SMPSK with MCPM. ASE is one of the important matrices for communications. It represents the amount of information transmitted per unit of time and per unit of bandwidth. Here, B is given by using the Carson's rule measure and the achievable information rate, AIR, denotes the mutual information between the channel input and the channel output. AIR depends on the median squared Euclidean distance between different symbols. Increasing the median Euclidean distance between different signals gives higher AIR. The minimum distance of MCPM and SMPSK are given in 4 and 5. We can see that the distance of proposed SMPSK is smaller and therefore it yields lower AIR than MCPM. Then next we focus on the B. We consider the MCPM and SMPSK has the same TS. Well, as two bandwidths through computation, we find that the bandwidth of SMPSK is narrower than that of MCPM by delta B, which is given in equation 6. Well, this results show that the modulation providing higher information rate is not necessarily the one providing narrow bandwidth. Additionally, AIR depends on the simulation-based BCGR algorithm. Therefore, it is difficult to derive a closed form result on which modulation methods is more spectrally efficient. Thus, we need a numerical simulation to compare the performance. Next, we will show the numerical performance comparison. Figure 3 shows the achievable information rate for different schemes. First of all, it is natural that higher modulation with higher transmission rate could achieve higher achievable information rate for high SNRs. We can see that the 16 modulation always performs better than the 8-phase shift key. Second, for low SNRs, the larger medium squared Euclidean distance, the less sensitive it will be to noise, and therefore the higher the resulting achievable information rate will be. It is clear that MCPM and the low-order modulation with larger distance can achieve higher achievable information rate for low SNRs. Next, we show the achievable spectral efficiency for different schemes. These results show that the modulation providing the higher achievable information rate, you can see here, is not that with the higher achievable spectral efficiency. We can see that both the16PSK outperform MCPM. In conclusion, we have proposed a novel precoder based on H016 phase shift key. We connect the precoder with continuous phase modulation modulator to generate a novel continuous phase modulation scheme named shaped H016 phase shift key. The analysis and the simulation show that the proposed modulation scheme can obtain higher spectral efficiency than conventional continuous phase modulation. Okay, thank you.